Before we get into topic 16, I just want to give you an overview of, the next five that we're going to go through here all constitute one big unit. In 16, we're going to talk about something called confidence intervals for proportions. In 17, then sticking with proportions, we're going to talk about what the term is tests of significance. And if you skip 18 for a minute, look at 19. We're back to confidence intervals, but for means, and 20 back to test of significance for means. So again, proportions come from variables that are categorical, means come from variables that are quantitative. And then thrown in there in 18, interesting topics. So just to try and give you an overview of the big ideas that we're going to work on here. Confidence intervals try and come up with an estimate of the population parameter. Again, a lot of statistics. We're trying to figure out something of interest, some number that describes our population. So that's a parameter. But we're going to use a range of values that we're going to do some specific calculations. So having a calculator handy would be a really good idea based on sample statistics. So we're going to take a simple random sample. We're going to crunch those numbers, come up with a statistic, and then use that to come up with a range of values where we think the parameter is in between. That's a confidence interval. And then we're going to basically put all of this, everything we've talked about with statistics together here. A test of significance is a way of determining, do the outcomes from our sample statistics help us prove that our idea is right. It's a way to assess the extent to which sample data, now it's going to be really strange how we set this up, refute a particular hypothesis considering our population parameter. Okay, so we're going to run a test to see if our results are significant or not. Okay, so with 16, again, we're going to deal with proportions here first of all, and unfortunately, we're going to skip the preliminaries this time. So if you're trying to follow along with me here with your textbook, I'm on page 332. We had talked about this, I think it probably was first quarter. There's an organization called the Kaiser Family Foundation. Back in 2004, they did a survey, written questionnaires. They got 2,032 people between the ages of 8 and 18 to respond to it. One of the many questions asked youths was whether or not they had a television in their bedroom, to which 68% answered yes. So the observational units in this study are American youths, ages 8 to 18. The variable that they're talking about here is whether or not that person has a television in their bedroom. It's a yes or no question, so that's categorical binary. Because the variable of interest is categorical and binary, the relevant parameter of interest is a proportion. So when they said the 0.68, is that a parameter or is it a statistic? Well, it's a statistic because it came from the sample. It's not the parameter because we don't know what the real proportion of kids in that age range have a television in their bedroom. So this is a sample proportion, so we need the symbol p hat. Part D, describe in words the relevant population parameter of interest in this study. Well, the parameter of interest was going to be the proportion of all people in this country ages 8 through 18 have a television in their bedroom. And again, that's going to be a proportion describing the population, and that symbol would be pi. For part E, does the Kaiser survey allow the researchers to determine the exact value of the parameter? No, it does not. We're trying to estimate it. Again, that's so much of what surveys are going to do from a statistical standpoint. We're trying to estimate what the population proportion is. For part F, is the central limit theorem for a sample proportion valid in this context? Well, yeah. The random sample, that's part. But then is the survey size large enough? Remember, we have to take the sample size n times p hat. Well, the 2,032 people that responded, 0.68, yeah, that's a little bit bigger than 10. But then remember also we need to take the complementary proportion. So again, this is the number they give us. Then we've got to take 1 minus that to find the complementary proportion. And even that, although it's smaller, is still going to give us a product that's much bigger than 10. We're good to go with our central limit theorem. So what does it all predict here? So the sampling distribution will be approximately normal in shape. It will be centered at pi, again, that population proportion. And we could say that the standard deviation is going to be pi times 1 minus pi over n. Our sample size was 2,032. Take the square root. Okay, so remember, the central limit theorem will predict for us three things: the shape, center, and spread. For part G, based on the distribution in part F, in general, how close do you expect the sample proportion to be to the population proportion? Hint, apply the empirical rule. Well, we're hoping that that sample proportion would be within 2 standard deviations of the value of the population proportion pi. Part H, based on your answer to part G, how close do you expect the population proportion to be to the sample proportion? Well, that's the whole idea here now, isn't it? We calculated something here from the sample proportion. How close do you expect it to be to the population proportion? So again, what I just tried to explain a moment ago, the purpose of building a confidence interval is to use some statistic that we got from a sample to construct an interval of values, again, a range that you can be reasonably confident contains that actual parameter, although we don't know exactly what it is. If we knew exactly what the population parameter pi was, we wouldn't need a confidence interval. Okay. A new term that you need to know here is called standard error. Okay. This should look somewhat familiar to you. We're going to take from our sample the statistic p hat, multiply that by 1 minus p hat, divide by the sample size of n, and take the square root. Okay. This is an estimate for standard deviation. Okay, standard deviation refers to the spread if we know the population proportion, if we know stuff, if we know parameters about the population, we know what pi is, we would know what standard deviation is. Since we don't know either of those, we're going to replace standard deviation with standard error. And yeah, that formula should look really, really similar as far as the the mechanics, the algebra of it. Very, very well. So for part J, they're showing you calculating the standard error from that survey. So we'll take the 0.68 times the 0.32 divided by the sample size of 2,032 people. So we'll get 0.01035. Again, arbitrarily, if they're deciding to go up to 5 decimal places, that's awesome. Now, if we go to standard errors, not standard deviations, two standard errors, which is just calculated for you there in part J, on either side of p hat. All right, so we'll take 2 times the 0.01035, and we'll add that to 0.68, so that's 0.0207. We'll add that to 0.68. And we'll come up with 0.7007. We'll take the 0.68 and we'll subtract the two standard errors, subtract 0.0207, and come up with 0.6593. That is a confidence interval. It's a range of numbers where we're reasonably confident the actual population parameter pi is somewhere in between those two numbers. Okay, so that's what we're going to do here. This is our confidence interval. How confident do you want to be? So if we go to our empirical rule, we know that one standard deviation to the left and to the right means we should have about 68% confidence that we have captured the actual parameter that we can't find directly. If we want to go two standard deviations, we can say that's 95% confident that we've captured the number that we want to in this range. We go three standard deviations, 99.7. All right, now, how about this? What percentage of Fenwick students are actually doing their online assignments on time? Well, I could say with 100% confidence, it's somewhere between 0% and 100%. I'm not wrong, but that's not really all that helpful, is it? Okay, I can be 100% confident that it's somewhere in this range, but that's not a useful statistic. It's not a useful confidence interval. Okay, so what we're going to do is try and do some calculations here and come up with something a bit more meaningful than that. All right, so how wide we want our confidence interval is going to be based on, our calculations here are going to be based on standard deviations, or more to the point, standard error. Because remember, this all part of it here is what we call the standard error. And it's used in place of standard deviation because we don't know it. Okay. This, you should know, is our statistic coming from our sample proportion here. And now the part where we need to have a little bit of discussion is on that guy, Z star. This represents a critical value from our standard normal distribution to get us the confidence level that we want. Okay, so that Z star is going to be a specific number. Okay, and we're going to put that in as part of our lovely calculations to create this confidence interval. All right. So activity 2 about critical values. Man, they walk you through it here and it gets really tedious, in my opinion. And this is what it boils down to. Using our inverse normal distribution function, okay, we can figure out for a confidence level of varying degrees, so we can make sure that we've got 90% of the data underneath it there. To do that, we would use a value there for z star of 1.645. If we're only going for an 80% confidence level, we would use the z star of 1.282. The 80% isn't used all that frequently. They will be asking you from time to time for 90. 95 is fairly common. 99% is probably the second most common. Okay. So, somewhere, maybe in your notes, write it on a post it. Put that somewhere around your desk there. You're going to need to refer to these numbers as we go through, again, not only this section here about confidence intervals with proportions, but we're going to come back to this and do confidence intervals with means. So you're going to need those z star values. Okay. Those will not change from one problem to the next. Okay. P hat will change, standard error will change, but the z star numbers will not. So if you want to write those down somewhere to have them for reference, that'd be a great idea. Okay, then for number 3 here, let's actually do this. Okay, let's actually calculate. So they told us here that p hat was 0.68 and the sample size was 2,032 people. So the first thing we need to do is figure out the standard error. Okay, so to do that, we're going to take the p hat value, the 0.68, and we're going to multiply that by 1 minus that. So the complementary would be 0.32 divided by 2032. Okay, so again, that's our standard error formula. Well, it was there in blue. This is the one I'm using here. So again, with our lovely calculators here, see if I can just do this all at once. 0.68 times 0.32 divided by 2,032 people. So that'll give us a standard error of 0.0103. Let's go to 4 decimal places here. 0.0103. Okay. Now, if they're asking for us to use this sample to construct a 95% confidence interval, so for my confidence interval, I'm going to take the value for p hat. I'm sorry, let me go back. Get rid of this stuff here so we can see exactly what's going on. We need to start with p hat, which, of course, in this case, is our 0.68. Now we're going to do plus or minus. Again, we're going to add this to get that upper value for our confidence interval. We're going to subtract to get the lower level for our confidence interval. And again, if you're on page 336, it mentioned a 95% confidence interval. So for 95%, we need a z star value of 1.96. So 1.96 times our standard error. Well, we just calculated that, so I can just simply substitute 0.103 right in there. So this is the value that I'm going to add to and subtract from the 0.68. So we start with 0.68 minus 0.020188. That's the lower level of my confidence interval, 0.68. And then I'm going to add 0.020188. And that's the upper value. So, I don't know, my standard error, I rounded that off to 4 decimal places. So I'm going to do the same thing here. So we'll say 0.6598, comma, and then the upper value there, 7002. That's our confidence interval. Based on the statistics from the survey, we're 95% confident that the actual proportion of kids 8 through 18 who have a television in their bedrooms is somewhere between 0.6598 and 0.7002. Okay? If you want to round that off even more, maybe put it in less technical terms, somewhere between 66% and 70% of kids have a television in their bedroom. Okay? And hopefully that sounds like something that you would hear on a news report. According to a recent survey, between 66% and 70% of kids have a TV in their bedroom. Experts say blah, blah, blah. Okay, so part A, I walked you through that. Part B, the interpretation, that's the words I just used. Can you be certain this interval contains the actual value for pi? No, you can't be certain, but we're saying we're 95% confident that the interval has that actual value. Does that make sense? Part D, now they want you to calculate the width of the interval, which simply means you're going to subtract those two values. Part E, they're going to ask you to calculate the half width. No big deal. Divide by 2. And the reason they're asking you to screw around with these numbers is because the half width of a confidence interval is often called the survey's margin of error. And if we actually do have an election later, you will be hearing all kinds of reports. And a recent national survey, blah, 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 the survey has a margin of error of plus or minus 3%. So that's what, from a statistical standpoint, what they mean for margin of error. Okay. By the way, that 0.0203, does that number sound familiar? I'm sorry, let me go back to. Now, depending on where you round it off, it's 2 times the standard error. That 0.020, well, we had 188. That's what we added to and subtracted from the sample statistic in order to build the confidence interval in the first place. So that number should correspond to the margin of error. Okay. The next thing they asked is determine the midpoint of the interval. Well, the midpoint of the interval should be, well, okay, so you take the confidence interval, add those two numbers, divide by 2. Wait a minute, that's the value for p hat. course that makes sense because we created this by figuring out here's the center point, here's what the statistic told us. We're going to add this critical value, we're going to subtract this critical value. Of course, it's going to be centered at p hat. That's how it was built in the first place. For part I, what technical conditions underline the validity of our lovely procedure here is, well, it was a simple random sample from the population of interest, and the sample size is large enough. And again, we crunched those numbers earlier. For part J, how would you expect, this is an opinion question here, how would you expect a 99% confidence interval to differ from the one that we have here, the 95% confidence interval? Now again, answers may vary. Hopefully you're thinking it's going to be wider, so it's going to include more values so we can be more confident that the actual value is in that range. All right, so then they tell you to calculate the 99% confidence interval. Now, the only thing that's going to be different here is that value for z star. Everything else is going to be the same. So now, for a 99% confidence interval, our z star number has to be 2.576. And again, hopefully you got that from the chart and maybe your post-it note. Crunch the numbers, again, add, subtract, so we get 0.653 to 0.707. Now again, compare. Here's the low end, 0.653. For our other, the low end was 6597. The 99% confidence interval is wider. This number is further from our central statistic. Okay, and compare here the 0.707 compared to the 0.7003 that they did. Again, it's further away. The midpoint's going to be the same. That's our stat of 0.68. And it's wider because it has a bigger z star. We're multiplying the margin of error by a larger value. As the confidence level increases, margin of error and width of the confidence level also increase. The midpoint has to be the sample proportion p hat regardless of that confidence level. So based on these intervals, does it seem plausible that 0.5 is the proportion of everybody? Well, no, it really shouldn't, because again, regardless if we're using, I'm sorry, let me take away some of these distractions here. So this is the 99% confidence interval. This is our 95% confidence interval. Can we say that the actual proportion, the value for pi, is 1/2? No, it's not in that interval. And it's not in the wider one either, 0.5. No, it's outside that. So we should not say that 0.5 is plausible. What about 0.75? And 0.75, in this case, that's out here. In the wider one, 0.75 is still out here. So no, that's not plausible. Could the population parameter be 2/3? In other words, 0.6666 repeating. No, 0.6. Yeah, that's plausible. I mean, that's in this interval. And again, 0.66666. Yeah, that's in that interval also. So that's why they're saying here 0.5 is not plausible, 0.75 is not plausible, but 2/3 is plausible because those fit in both the 95 and 99% confidence intervals. The survey also provided sample results broken down separately for boys and girls. So there were 1,036 girls, 996 boys in the sample. Among the boys, 72% had a TV in their bedroom compared to 64% of the girls. So they're asking you to find a 95% confidence interval proportion for American boys, blah, 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 blah. I'm not going to make you, I'm not going to do the calculations. You can do this on your own if you want to practice. Key things here are, again, they said 95. So our Z star there has to be the 1.96. They gave you differing numbers. That boys was 72. Okay, so the 72 here and the 72 here, and then the complement of 0.72, the 0.28. For the girls, it was 64, so the 64 is here, and its complement. And again, the sample sizes were different for boys and girls. Okay. All right, so let's go back to the creepy stuff. Remember this? The kissing couples thing. 124 kissing couples were observed. 80% of them leaned their heads to the right. The observational units were the couples kissing. The variable was which direction. So again, that's categorical binary. It's either to the left or to the right. So this is yet again an example here where we can do a confidence interval for proportions. Sample data consists of the 124 kissing couples observed, and again, 80 of them leaned to the right, so 80 out of 124. Our value there for p hat is 0.645. Like you needed to see that little pop-up about the email. So the graphic display here is, all right, here's number of couples to the right, do the subtraction, number of couples that lean to the left. Determine and interpret a 95% confidence interval for the proportion population, blah, blah, blah. All right, so 95%, hopefully, again, we're getting used to seeing the 1.96 as our Z star value. So we get the 0.645 from the information in the book. And our complement here, that's a terrible typo, isn't it? Let me see if I can patch this up for you now quickly. Take the 1 minus the 0.645, divide by, again, the sample size there was 124 kissing couples. Again, that underneath the square root, that whole part of it there is our standard error, not standard deviation. So then we'll get a lovely little confidence interval here. We are 95% confident that the proportion of all the people kissing in public lean to the right is somewhere between 56% and 73%. Okay. Now, let's make sure that we understand that 95% confident phrase. If we take random sample after sample after sample, generate a 90% confidence interval from each, in the long run, 95 of those resulting intervals would be successful in getting the actual value of the proportion of the entire population who lean their heads to the right when they kiss. Before I get to the assignment, several of you have asked through email, wait a minute, I always borrowed a calculator from New. Now you what? Okay. Um, I don't know what you guys can find at your house, but if you do have interwebs, type in Desmos. Now, for those of you that have had Mrs. Keller for class before, she swears by this. And I have some other preferences when it comes to doing the geometry side of things. Desmos is terrific as an online graphing calculator. It can do amazing stuff for you. So if you've not tried this before, I suggest desmos.com, and then you click on the big red, is that red? Big red button here that says start graphing. Now, you really don't need the graphing part of it here, but it's the calculator functions that are terrific. Now, if you want the little calculator keyboard to show up, you can click on that down at the bottom there. But again, just to construct our confidence intervals, you can use your keyboard, the point, I don't know, I'm just making this up, 0.68 plus, then we took our critical value of 1.96 and multiplied that by our standard error, which was 10103. Now you notice here, you don't even have to hit enter. It shows you the result of that calculation right down here. Okay, so again, if we're building that confidence interval, it's got to be the p hat plus or minus the blah, blah, blah. So you can just use the backspace key, get rid of that addition symbol, put in a subtraction symbol, and again, there's that other answer for you right there. So Desmos is a terrific online calculator. It will also do the probabilities from the normal graph and the inverse probabilities. If you've got the z-score and all the rest of that I taught you guys how to use the n-spires and TI-84s to do. On this, obviously you don't have this huge keyboard like we do with the n-spire. It has tons of functions for you, including things like, oh, look, statistics, the quartile, standard deviation, correlation coefficient, we haven't even gotten to yet. Um, to use those, I would say, you know that there's a YouTube video for just about everything in education, right? So yeah, if you just do a quick search on the interwebs about finding standard deviation of a normal district, I mean, you'll come up with all kinds of really short, simple, clear videos that'll tell you about, but for Desmos and some of the technical things with statistics, you have to know what it is, the formula that needs to be typed in there. So, but again, there's all kinds of lovely videos online so that you can use that. Okay, so for your assignment here from topic 16, this should start in your book on page 347. I'd like you to try numbers 9, 10, 11, 12, 13, and 14. Hopefully that's not too hard to remember. If you're having trouble filling the hours for exercise number 9, part A tells you flip a penny in the air 50 times and keep track of how many heads and tails results. And then you're going to construct a confidence interval on that. You can use your calculator, you could use your computer to run a simulation of those 50 coin flips, or If you want to flip a coin 50 times, yeah, you go right ahead. Please try not to do it in as a way of deliberately irritating somebody else in our. They're not. The governor doesn't want to call it a shelter in place. Um, Please, my homework said I had to flip this 50 times, so you just be quiet over there. 22, 23. Okay, so just be nice. Please be kind. Um, so yeah, hopefully again you can do this on OneNote so I can see what you're doing. And as you go through this, not quite sure, send me an email and I'll make another video showing how to go through all of those answers. Good luck, everybody.